Right, so welcome to the second lecture of the day. Claudia Miller is speaking about algebra structures of linear solutions.
Thank you. Okay, I'm a really slow lecturer, so I'm always worried that I'm not going to finish, okay? But despite this, I set my alarm for 45 minutes so we can have a 2-minute break or something in the middle. Okay, maybe longer than 2 minutes? Okay, all right. GG algebra resolutions. That's resolutions, that word, okay? Can you ask me if you don't know one of my abbreviations? Because I abbreviate a lot. Okay. All right, so, from last time, some corrections. The Horrocks conjecture was also sort of independently proposed by Buchbaum and Eisenbud in slightly greater generality, and so it's actually called the Buchbaum-Eisenbud-Horrocks conjecture. I forgot to say that n is finitely generated and non-zero, or it doesn't make sense, or it's not true. And then in the lifting lemma, I forgot to say that you need the module. Oh, I don't know if it was called M. It might have been called F. Yeah, maybe it was F. You need that bounded below, which means that you need Fn to be 0 for negative stuff, like large negative stuff or all negative stuff, whatever. At least stop. And I mainly forgot to say that there's this wonderful book paper. It's between a book and a paper by Abramov called Infinite Free Resolutions, and it's just wonderful and it takes forever to read. But I'm getting a lot of my material from that, almost all of it. So if you want to read more, see some good proofs, and read everything, and there's much more in here, that's a great place to look. And so are all these, many old papers are very beautiful, papers of Gullikson, many papers. If you want to know what papers, this tells you also what papers to read. So this is a great source. Okay. All right. So last time, we learned what IBG algebra was, and we also looked at minimal free resolutions, and we discussed that sometimes they have a DG algebra structure. We did an example. There's some results that say you have one, and then there was some motivation for why you want to have one, which is the Horrocks conjecture. And then we saw there were counterexamples. Sometimes you can't put a DG algebra structure on the minimal resolution. Okay? So today, we're going to go non-minimal. We're going to go away from minimal and make a very big resolution that always has an output. All right? So the main point today is given an R algebra S, which is the same as, so first place, this is going to be R mod I often. It doesn't have to be, but it's easier to talk about it when it is, so I'm often going to do that. I'll tell you a bit about what to do when it's not quotient. So you have an R algebra S, i.e. what I really mean is that you have a homomorphism from R to S of rings. Okay, that's the same thing. Oh, and it's usually called phi. Okay, so we'll build a free resolution, usually far from minimal, with a DG algebra structure. So it's going to have a product. Okay, but besides that, it's going to be even better. Even better. it will be sort of free. In what sense? Well, we're talking about algebras now, so we want it not to be free as a module. Well, it will be, but as a graded, why did I write graded? What happened to me? Oh yeah, sorry. Graded commutative, which is graded commutative just means this A, B is minus 1 to the A, B, B, A. So it means commutative up to sign. Is a graded commutative, as a graded commutative algebra. Okay, so what do I mean by that? Well, if you just ask someone in math, give me a free algebra, they're going to take a ring and they're going to adjoin variables that do not commute. They're going to give you a non-commutative huge, right? That's called a free algebra. But we don't want that such a large thing because we're in the world of commutative algebra and algebraic geometry. So we do want some commutativity, so we want this. So if you don't take the free algebra on variables that just do whatever, but if they actually commute or anti-commute, then that's like, so this is like a poly ring, a polynomial ring, or exterior algebra. Okay, and so, we'll have a combination. It'll be both polynomial and exterior. Okay, and so how are we going to do this? So let me just tell you the vague idea for a second. This is very vague, so it's okay if you don't follow this. For each n, and we're going to do this inductively, 0, 1, 2, 3, okay? So for each n, if Hn, the nth homology of the complex that you have built so far, up to now, so if at that stage the complex that you built has an nth homology that is not equal to 0, so then you look at it and you say, well, how big is it? So you pick some generators for it. So you choose, actually, cycles in the complex. So what's cycles again? These are things in the kernel of the differential at that point, nth differential. You choose a bunch of cycles that when you go to the homology, which is kernel mod image, that they generated. So generating Hn. And so the reason that they're not 0 is they're not boundaries, right? They're not the image of anything. So you just make them the image of something. So, I should have given some names here. Cycles. Let's call the set of cycles Zi. It doesn't matter really. So when you do that, you adjoin variables, let's call them xi. Okay, and so this was in degree n. So if it's going to be the image of something in the complex, it better be coming from something in degree n plus 1 in the complex. So these are of degree n plus 1. So we're just throwing stuff in, some variables, that we're going to force to map to these. So, and define the boundary of xi to be zi. And now the zi's are boundaries. So now the zi bar in the homology, the quotient, are 0 in homology. Okay. Okay, but we want to keep having an algebra. So if we want an algebra, a DG algebra. So if you put in xi, you have to put in xi squared. You put in xi times everything else that's already there. You have to put in the whole entire algebra generated by xi. So you need to, make the entire algebra generated by the xi. Okay, so that's what we're going to do. And I could just do the theorem and say you can do this, but I just want to do an example because it's so weird when you adjoin something, but you also get all this garbage. Get xi squared, which has a bigger degree. So I want you to see it. Okay, so we're going to do an example first. Okay. So let's see this in action first before I just give you the theorem and the proof. Okay, so this is going to be the running example. Everything I talk about will work for this example. So I'm going to just keep using this example a lot this week. Let K be a field, always. Let R be K adjoin xy mod x cubed plus y cubed. And the algebra we want to look at, that's the base ring. I want to surject onto the residue field, K. So in other words, R mod xy. Okay, so technically speaking, all my lectures are over local rings. Although I think a lot of stuff works over graded, but it's a little harder to find where things are written. So we should either localize this or make it a power series, and it's much easier to make it a power series by drawing 2 lines, so I'm just going to do that. But I sometimes forget to do that, so just excuse me. Okay, this thing that I modded out by, I'm going to call I later today anyway, so let's do that. Okay, step 0 is the way you always resolve. How are you going to resolve R mod something over R? You start with R, right? So you start with the complex R, and then that's the whole complex. So this is in homological degree 0. I'm just going to put a little 0 up here. And then I have K, 0, and this is epsilon. This is just the augmentation map, which is just the projection to K. Okay, so you always, the first beginning is a little weird. You just map onto it, project onto it. And then, I don't know, people talk about so we're going to eventually chop this off, but I think it's easier to just think about it there still. So now I'm going to start doing this. I'm going to look at homology. If it's not 0, I'm going to join some stuff. Okay, what is H0 here?
Ideal.
It's the ideal, right? It's the kernel of the map is this ideal I, generated by X and Y. Okay, so the second step is, which I guess I'm still calling this step 0, I guess. Okay, is, why did I do that? So let's adjoin some variables. So those are the 2 generators, right? X and Y. 2 gens. Okay, so and that's degree 0. Let's adjoin variables of degree 1 to kill these cycles, is how we say it, to kill these cycles, X and Y. Okay, so let's call them, fine. These variables of degree 1, I'm going to call them E1 and E2. And I want to define the boundary of E1 to be x and the boundary of E2 to be y. Okay, but now I actually want to throw in the whole algebra generated by these variables. Okay? What kind of an algebra is it? They are degree 1 variables. So what kind of an algebra does this form? Do they commute? So these are degree 1. So E1 times E2 equals minus 1 to the degree of E1, degree of E2, E2, E1. 1 is negative, right? So it equals minus E2, E1. Sorry, that's minus. Whatever. Okay, so these are what kind of, and also E1 squared is, well, you can commute E1 with E1, minus 1 to the E1 squared. I've traded the two E1 factors, but that's negative, is minus E1 squared. Okay, so if characteristic is not 2, that tells you that that's equal to 0. Okay, so actually though, it's not just that we want to be commutative, we force the squares to be 0 in characteristic 2. So anyway, what do we get here? What kind of an algebra? I'm hard of hearing, sorry.
Exterior.
Exterior. Okay, so this is an exterior algebra. Okay, so we get the exterior algebra. Because of that, so this is really like R. I'm going to put a square bracket. It doesn't matter. I'll tell you about that later. E1, E2, we've adjoined them such that the boundary of E1 is x, the boundary of E2 is y. What is this called? Have you seen it before? Sorry. Koszul complex. Okay, so now we need to look at it, right? I'm gonna write it out. Sure. Okay, we still have the k at the end. Let me put it. Okay, so we have R where the basis is 1. Then we have some. I haven't put the exponent yet. What do we have in degree 1? What's the basis? E1 and E2. So this is R2. What do we have in the next one? Degree 2. E1 times E2. So that's all you have, right? Because squares are 0 and that's it. So R to the 1. 1. Okay. Questions? Okay, so that's the Koszul complex, and okay, well, we know where the E1 and E2 go. E1 and E2 go to x and y. Where does this go? Under the boundary map. These are boundary maps right now. So what's the boundary of this? So you take the boundary of E1, which is x times E2, minus, because you go over a degree 1 element. E1, boundary of E2 is y. And I'm going to put the y in front. There, because it commutes. Okay. Good. So what's the next step? We killed the zeroth homology. There should be no zeroth homology here anymore. This is 0. This is position 0. This is position 1. This is position 2. Great. Is it exact here now? Yeah, the kernel is x and y, generated by x and y, and that's the image here, so it's exact here. It's not exact here. So we have to find, oh, I know this. You don't know this yet. It's not exact there. The reason is that x and y are not what on R? It's not a regular sequence on R. So if you know that stuff. So somehow there should be some homology here. Oh yeah, so this should be called step something, 1. So what is H1? Okay, there's some obvious stuff that goes to 0. Like ye1, oh, that's not good, I'll get back to you. So ye1 minus x e2, okay, but that's in the image. So that's the Kazul, it's called the Kazul relation. So, okay, let's see, so there's ye1 minus x e2, but that's already in the image of the previous delta. As you can see, it's the negative of this, so that's not good. So if you were over the polynomial ring, this would be it. So it has something to do with the fact that we have an equation.
Yeah.
Good. So now, this is 0. So can you tell me, now I'm getting back to the people who were saying something that I wasn't listening to. Can you build me, we know this is 0. And we know that e1 and e2 go to x and y. So what? X squared e1, because that will go to x cubed, right? That's good. Plus y squared e2, because that will go to y cubed, so, and this is 0. Okay, so that's in the kernel, and that is actually the entire kernel. So there's actually a theorem that tells you that the kernel is generated by the obvious things you can make out of these. Okay. So actually, there's just one thing. So there's this guy. So there's one, it's one generator. Namely, that's the generator. And so that's sitting here, and it's not happy because it's not an image. So we have to put something here in degree 2 to hit it. Okay, so adjoin. Sorry, my names of variables are weird. I'm going to call it t. T of degree 2 now. Degree 2 variable. And set the boundary of the differential of t to be exactly that thing that we didn't like. X squared e1 plus y squared e2. Now it's an image, and we're fine. Okay? So now let's write down what we have. But we have to put the whole algebra in. So this variable has degree 2. So what can you tell me about whether it commutes or anti-commutes with other things? Commutes with everything, right? Okay, so degree 2 is even. So it commutes with all. Okay, so this is a polynomial variable. Okay, so it's a poly variable, by which I mean we're adjoining the entire polynomial ring. Okay.
Next step is going to be infinite.
It's going to be, the next step is infinite. Very good. It's already infinite now. So let's write down what we have. So we have R. We adjoined E1, E2, and T. Okay? And I'm lazy, so I'm just going to write this goes to X under the boundary map. This goes to Y. And this goes to X squared E1 plus Y squared E2. Okay? All right, so this entire algebra, and this notation is understood that this is the exterior algebra generated with these, by these, and the polynomial ring generated by that. Oh, sorry. Let's put square brackets. Sorry. Okay, square brackets. Okay, and the definition of this is really, it's the first ring we made, which was the Kazul complex, the exterior. So this is an exterior algebra. Tensor over R with R adjoin T, and this is a polynomial ring or algebra. Okay, so that's just what we mean when we put them all together as a list. We mean this, but it's just all the things you could form from these. Okay, now we need to check. So hopefully H1 is now 0, and we need to check H2, but I need to write the complex out. So let's write the complex out. So let's check. Well, here's what we have. We half. Okay, so I have a K, I have R, I'll put the basis down below. I have R, so what do I have in degree 1? I have E1 and E2, right? And any products, but there are no products that give you degree 1. Okay. How much, so there are 2 things here, so it's R2. What do I have next? Oh, in homological, I should write the homological degrees. This is homological degree 0, 1, and 2 so far, and then I'll do more. 3, 4, whatever. Okay, what do I have of degree 2? Yeah, E1, E2. I heard someone say that. E1 times E2. T. So that's the basis here, so I guess I have 2 things. So it's R2. Next. E1, ET, good. E1T, sorry, and E2T. Squares? Not allowed. E1 squared is 0. E2 squared is 0. T squared is too big. T squared is degree 4. Oh, sorry. I'm going to move this over a little bit. We're in degree 3. So I have 2 things here. What do I have in degree 4? T squared. E1, E2T. Yeah, I know. One always forgets. So actually, it's starting to repeat. You have whatever you had 2 steps before times T. 2 steps before times T, right? So anyway. All right, but this goes forever. So I'll put a big dot, dot, dot. I think I decided to write what it looks like. So we need to figure out the homology. So let's actually write the matrices for the maps. So the point is that it should be exact in degree 1 now because we added the T in. But this degree, we don't know if it's exact. And it might not be. Okay, so I need to know what some of these differentials do, especially right around here. Okay, so the differential of E1, E2, we already wrote somewhere. Here it is. And the differential T, we wrote here. So writing those as the 2 columns, man, where am I going to put this? Let's call this matrix A and this matrix B, the 2 surrounding here. So this is A, and this matrix I'm going to call B. So A, we already computed. The first generator is E1, E2, which goes to this thing, so minus Y, E1 and X, E2. I'm writing in terms of the basis E1, E2. And then another one, the T went to X squared and Y squared. Okay, we need to compute B, so I need to know where E1T and E2T go. So boundary of E1T is by Leibniz rule. I forgot to say, so let me say it here. You adjoin the variable, you define the boundary to be whatever, and I should have said, and extend boundary by Leibniz. Okay, so this is X, T, because the boundary of X, and then minus, because it moved across the degree 1, which is odd. E1. Oh yeah, so X squared E1 plus Y squared E2. Yes, E1 times E1 is going to be 0. Right, so I just get XT minus E1, E2. Oh, there's a Y squared. Thank you, E1, E2. Okay, so the matrix, okay, and then the other one we can just guess. Boundary of E2T. So the matrix B is going to, the first column is coming from here. And I wrote it in the order E1, E2, and then T. So let's put the same order. So I have a minus Y squared and X. And the other one will give you minus X squared and Y. So those are the two matrices. Okay, so what's the homology now in this spot? Step 2. I'm kind of losing track on the counting. Okay, yes, H2. It's kind of harder, isn't it? Okay. Yeah, I know what you're going to ask. Oh.
There's a question. Second row from the front, there's a question.
There's a question.
Oh! Yeah.
In the resolution for module 4, should that be R2 since there's 2 generators?
Yes, they should all be R2. Thank you.
Except for 0.
Except here at the beginning should be R1. Good. Okay, thank you. Okay, I'm not going to do this. You can do this, but it turns out that this is 0. And in fact, all of them are 0 at this point. So H bigger than or equal to 2 is all 0. I mean, this is a result of tape that we're going to see later today in the afternoon. And so we're done. We have an infinite resolution, but it's done. Okay? So that's the resolution. So done. And it has an algebra structure. Look at that. Because it's an algebra. With a DG algebra even. Okay, oh, one more thing I want you to notice is that AB, in fact, there are lifts of the two matrices A and B to the original ring, to the polynomial ring K of xy. In fact, actually, you just lift them to what you see on the board. Those, these are really cosets, but just lift them to these particular things. Such that A times B is the equation we started with, x cubed plus y cubed, for defining the ring, times the identity matrix, and that's also equal to B times A. So that's a structure. That's a structure that Eisenberg discovered, and it's called a matrix factorization. Matrix factorization of this element here, x cubed plus y cubed. Okay, matrices that multiply to identity with that on the diagonal. So there's a whole bunch of structure hidden here that I will tell you a little about later today. But what else do I want to do right now? Oh, so I lied. This is not correct. Unless you're in characteristic 0. So if the characteristic of K is 0, you're done. If it's not 0, this doesn't work. And did I want to talk about that now? So I think I'll just talk about that as I go. So instead of adjoining a polynomial variable, so in characteristic P, we actually need to adjoin a bit more. They're called divided powers of T. So that T that we adjoin is not quite enough to kill further up here, to kill all the cycles and make all the cycles boundaries. But if we adjoin something called divided powers of T, it will be enough, and then it will be a resolution. Okay. And so that's why I put square brackets, is we were just adjoining polynomial right now. Okay? But if we join divided powers, we'll start putting angle brackets. Anyway, that's what I'm going to explain next. Okay, so do you have any question about this example? Oh, one more thing. This continues. A, B, if you compute it, this is A again. It's essentially because these basis is T times this basis, and this basis is T times this basis, so you can show this is the same matrix again. And then B and AB, ABB. So it's infinite periodic of period 2. Okay, any question about this resolution? what I did. Okay. All right. So I think I'm just going to now talk about this very generally and give the theorem eventually. But first I want to formally describe adjoining variables properly. Adjoining variables. To kill cycles. Okay, so let A be a DG algebra. So you should just think of whatever we had at a certain stage. Like at one stage we had R adjoined E1, E2. And then we adjoined, that was a DG algebra, and then we adjoined a variable T to it. Okay, or at the 0th stage we had R, and then we joined E1, E2. Okay, so you have some DG algebra, and you have a Z in degree n, so in AN, a cycle. All right, so if n is even, okay, you want to kill it, so you want to adjoin a variable of odd degree n plus 1. So you always have to join the variable one further along in the complex so that it can map and kill that thing. Okay, but that's now odd degree. And odd degree
Very quick question. I think in B, x squared is a minus, right?
really?
Because you have to commute.
Oh, because E1, E2, you get E2, E1, which is really E1, E2. So the x squared should be positive here. And what about this? Was okay because it's in front of the t? Okay.
Okay, thank you.
Thank you. So that the B matrix should have a plus x squared in it. Okay. Which of course it does in my notes, but I don't look at my notes. Okay. So we're going to join a variable of odd degree, which means it is what type of variable? Exterior. So this means it is exterior, meaning it forms an exterior algebra. So we can call this, like we did earlier, A of x, or we can call it A of x with an angle bracket. It doesn't matter either. What's going to matter is the even degree ones, and so whatever the even degree ones are, we'll just do this. So same for these, so it doesn't matter. So what that is, it's the exterior algebra, so that's got A, and it's got AX, but then it doesn't have x squared to 0, right? X is in, oh, did I tell you that the variable is called x? No, adjoin a variable x. So it's odd degree, so it's square 0. So that's it. That's the whole algebra. There's nothing more. Okay? Right? X squared is 0. Okay? If, on the other hand, n is odd, so you started with a cycle in odd degree, you have to put adjoin. So either 1, like we were doing, a variable x of even degree, n plus 1, and because it's even degree, this is so it's a poly variable, a polynomial variable. And we write this as A adjoined, just the way you always write the polynomial ring. And the polynomial ring over any algebra A can be broken down as A plus AX plus AX squared plus ... Okay, so that's one thing we can do, and it works okay in characteristic 0, but there are going to be problems in characteristic P. So here's a better thing we can do, or 2. We can adjoin what's called a divided power, well, it's not really called a divided power variable. It's called a divided power algebra, but I'm going to just call it that. Okay, and my note said it was better. A divided powers of a variable x. Okay, that's better. So what that means, and I have to tell you what those are and how they behave, but now we're going to use angle brackets to denote it whenever we have divided powers. And so you're going to have an a, and then you're going to have an ax, and then you're going to have an ax squared, but actually it's a parentheses around it. It's not quite x squared. Plus ax again divided 3 and so on. And actually there's an invisible 1 here. Oh, I'm supposed to give you a break, but I'm not giving you one yet. So there's a 1 here. So that's really like x to the 0. And there's this x to the 1 is really like x divided 1 is the same as x to the 1. It's this. Okay. So there's this, and I need to tell you what they mean. So how is this in algebra? So with the range structure, so I'll just tell you on the basis what it does. So if you have x to the L divided power, that's an L, times x to the m divided power, the definition of this is going to look weird at first. It's L plus m, choose L, times x to the L plus m power. Why is that? So what's really going on, and you're going to explore this in the exercises. For an example. So what's really going on is x to the L, it behaves exactly like, so it behaves like x to the L divided by L factorial. Now, unfortunately, so things like this would behave if it exists. So, if you're in characteristic 0, you can divide by whatever you want. Sorry, equi-characteristic 0. So if you have the rational numbers around, if you have x to the L, you have x to the L over L factorial, and it's fine. So then, this whole algebra is, so if R is if the whole thing is equi-characteristic 0, then a divided algebra, it has all of these, but these things that behave like this, well, you can show that's the same isomorphic to this algebra, the polynomial ring. So by adjoining these guys instead of regular powers, it's no difference. But if you can't divide by some number, like in characteristic p, you can't divide by p. These really are different, and you're not really dividing by this. It's just you're putting something formally, you're placing this formal thing there, and then saying, but pretend it behaves like this would have behaved if this existed. So in particular, that's where this comes from. If you take x to the L over L factorial and m over m factorial, you will get this choose times xl plus m over L plus m factorial. Okay? Obvious. Yeah?
So how do you decide which one to do this, except for the characteristic?
This week. Along the week, this week, we will find uses for both of these. So, yes. So, right. So this is so the divided one is more efficient because you don't have this problem that it actually then the homology would be dead in this example in characteristic P, and it's more efficient. So this one is better in that it kills more homology and it's more efficient. But it's actually true that this one plays a role also sometimes. So it's a long story that we will see this week.
question. So
Yeah.
if I never heard about this, and I was working in positive characteristics, so you said before that the H2 wouldn't be 0.
It wouldn't be 0, but if we had a divided variable, it would be 0.
Yeah, but maybe I never heard about this, but I was trying to do the resolution. So I find out that H2 is not 0, and I try to do like a further step.
So then you join t divided power 2, t divided power 3.
No, imagine I don't know.
Okay, then.
So I look at the H2, and
Yeah.
I'm trying to add another polynomial variable.
Oh, yes.
Only using the first two tools. Can I do
So
that?
yes, you can just use the first two rules and resolve. I will cover that next. Yes, you can always just use these two rules. It's just it gets very, very large in characteristic P, more than you need it to, and sometimes this fixes it. So I'll get there. Okay. And in fact, people don't actually know very much about how they're related, except for a recent result of Josh, that your TA, that tells I'll mention everything later. Okay. That in some cases you do know how they're related, the two procedures. Right. Yeah.
Did he satisfy a universal property?
Yeah. Yes. I'll get there too. These are really good questions, and they're all things I will get to. So, I'm supposed to give you a break. Okay, take a 1 minute break, even if it's okay, maybe 2 minutes. Okay, so I told you when you adjoin a variable, you get this nice algebra, either a polynomial, exterior polynomial, or divided. But I didn't tell you what DG algebra is. I didn't tell you the differential yet. So here's the differential. It's extended from whatever you had before. So the differential in the complex A, which I'm just writing differential A. And then you adjoin the new guy. So you have to say what is the differential of the new guy, and you say that it's exactly Z. That was the cycle. That was the cycle we wanted to kill. The cycle to kill. So now kill, it's a boundary. But in the divided power case, I have some more mysterious things, and I need to tell you what the differentials of those are. Well, x to the something acts like this. So just take what the differential of this. Okay, so let me write more stuff down. So this extended from these two via Leibniz rule. And and I need to also tell you in the divided case, and for divided, we also need to define the boundary of x to the n, let's say, is, so we have to define it, it's not given to us, is x to the n minus 1 boundary of x. Okay. Before I explain that, let me tell you in the not divided case, the polynomial case, or anything actually, is, by the way, the Leibniz rule tells you that's like it's like the product rule in calculus, right, with a sign. So it acts like the product rule in calculus gives you the power rule in calculus. That the differential of x to the n is n x to the n minus 1 chain rule times what the differential of x is, and you can totally prove that from the Leibniz rule. Oh, I should say for x even, so that otherwise it's sort of there's nothing there. Even. Okay, but if you divide by factorial, so if you do x to the n over n factorial, you get n x to the n minus 1 over n factorial. The n's cancel. It's x to the n minus 1 over n minus 1 factorial. That's this. So this is what this should be if it's a good world. This is not equal to blah over factorial, but it should behave exactly like that would behave. So that's why you define it. Okay. So you get this nice DG algebra. So I should have said these are all DG algebras. And if you repeat this a bunch then we often we set capital X to be the set of all, this is like a notation we use a lot, all the variables adjoined, except sometimes we use a Y or something else instead. So anyway, we use a capital letter for all the ones adjoined, and we call X sub n is all the ones of degree n. Okay, that's just notation. Okay, so now another definition. This kind of an extension, doing this over and over again, is called something. So if A, e.g. the algebra, a semi-free extension. Let me write this. Extension. Now, so the secret here is the word extension. It's not just semi-free. Semi-free is kind of boring. Most of the times it's just things are free. This is saying it's like free as an algebra. Like variables have been in. So this is sort of saying variables adjoined. Okay? So a semi-free extension, or in parentheses, I have to define it. A semi-free gamma extension. And so the letter gamma is going to now forever denote divided powers. It somehow became the code symbol for divided powers. I don't know why. I wonder if it's because of the gamma function. I don't know why. Okay. So anyway, is something like that up above. Is an extension of A obtained by repeated adjunction of, so in the first case it's of exterior and poly variables, and in the parentheses it's of exterior and divided power of variables. Whatever. That's not good English. Okay. All right. So if you keep adding on exterior and either divider or polynomial, you'll get the two construction. So as you can guess from the example, you can always do this to kill all the homology, and you get a nice resolution. So let's just write as a theorem, even though you pretty much know this from the example. Oh, wait. I want to say something. So in the example that we did, we were looking at H2. Okay? And so in characteristic P, it starts having problems. So, H sub 2 of, and I think we had R, adjoin, E1, E2, and T. Okay, so H2 is 0 in characteristic. So in characteristic P, so let's say in characteristic P there are problems. So for example, e.g. in characteristic 2, and you can explore this much more on the problem sheet, but I just want to kind of say a little bit here. There are two kinds of problems you can have. So the problem is you adjoin T to solve something. Namely, you adjoin T of degree 2 in order to fix a homology in degree 1. The problem is you create some garbage, some homology up higher up that's really kind of wasn't there before. So you're creating new homology. So here are the two kinds of things. T times the boundary of T and T squared are both cycles. Okay? Why are they cycles? So the first one you can just compute, but the second one, the reason it's a cycle is here. You take the differential, you get a 2 in the front, right? And so a characteristic 2t boundary of t. So 2 is 0, so this goes to 2t, 2, that's a 2t boundary of t, but 2 is 0. So that's a cycle that just suddenly appeared. Okay, and then you might think, well, maybe there's already something around that'll help kill it. Okay, well, the thing that might help kill that is almost t squared, because if you take the differential of that, you get 2t boundary t. Oops, I have a 2, so I need a half, and then it will hit it. But I can't do that in characteristic 2. So, impossible. So you can't, the obvious thing doesn't map to it, in fact, nothing does. And this has the same kind of problem. The obvious thing, well, this is a little more mysterious, but something should map to it, and you can't find something that maps to it. Okay? But if you do divided powers, these kinds of problems don't show up. And I will talk about that in the afternoon. But divided powers, if you join divided powers of t, then you get all the h bigger than or equal to 2 equal to 0. Bigger than or equal to 2. Okay, and I'll talk about that in the afternoon. Question? Yes?
Just to make sure I understand the sentence grammatically correctly, you say that, like, in that example, R adjoining E1, E2, and T is a semi-free extension of A or?
Of R.
Of R, okay.
Yeah, but it's also true that T, this is also a semi-free extension of R adjoining E1, E2. You can take R, E1, E2 and call that A, and then adjoin T. And along the way, we did that, so I just wanted to define it for any base thing that might be bigger than a ring.
So we still get DG algebra as we adjoin variables along the way.
Along the way, and then each time you adjoin one more, it goes DG algebra, you get a new DG algebra. Yes. Okay, so the theorem is that you can always do this. This is essentially take the divided case because that's kind of better in general. So, okay. If given R to S, P, is there a question? Or? Yeah.
Sorry, when
Yeah.
we have variables, like in the case where n is odd, do we need to choose one with the method 1 and the method 2 for every step, or we can also mix it?
Or you could say it again. So if you suppose you want to join, say it again.
At the step n, I choose to add polynomial variables. At the step n plus 2, do I need to choose again a polynomial variable?
Yeah, you need to take the new thing that you have, look at it as a complex, and it's exact where you fixed it, but the next point you have to look.
No,
What the
I
hell?
mean,
No.
If I need to add more variables in the step n plus 2, let's say in the step n, that was odd, I add variables polynomials. In the step n plus 2, do I need again to add polynomials, or I can also choose?
Oh, that's a good question. I see. Can you mix and match? Can you add polynomial and then add divided? You can do anything you want. That's true. Yes. Yes, you can. And you can resolve. So you can get a mixed resolution. And I don't think people do it a lot just because they don't know what to do with it, but you totally can do it. It actually does happen a bit when you're trying to prove this one theorem. So yes, you can do a mixture of things. Very good. Okay, so let this be and I'm going to take a surjective map because it's just easier to explain, but I'll tell you what to do when it's not surjective also. So that's a surjective ring map. These are all ring maps. Ring map. And let I be the kernel of it, kernel of phi, and so the statement is you can do this. So there exists a semi-free extension resolving S over R. Let me write it down. So write it is the following. We take the original ring R, we adjoin a bunch of variables. I think I decided to call them Y in this part, sorry. And this is supposed to now be the resolution, so this is a quasi-iso. And you're supposed to be resolving S. And here's the original math. So in other words, we built this thing, and it's a quasi-iso to this boring thing sitting in degree 0, which means in degree 0, the homology is S. And in degree positive, the homology is 0, so it's exact. So it's a resolution of S. Okay, that's just our usual notation for it. So you can do that, and you can do the other thing also. There exists a semi-free gamma extension resolving S over R. And so we write it in a similar triangle. So R goes to, let me call the variables X here. And then quasi-iso to whatever you're resolving, S, and then P. So there, you can do this. This guy, the first one is called, it has a name that I always forget to use. It's called a resolvent. And this one is called a tape resolution. A tape resolution. And you can do either. And as by your suggestion, you can also mix them and do that. Okay, so the proof is, I don't need to give you the proof. The example that we did is the same procedure for proof for this. You kill the homology successively, but I'll just write something. So as in the example, it's sort of inductive process. And the first one's a little weird. Always, first you adjoin degree 1 variables with the boundary of x1. So that's a big x1. That's all the degree 1 variables. That's the set of degree 1 variables, all of them. Boundary of all the degree 1 variables generates I, which was the kernel of P. Okay? And then you keep for each n adjoin variables of degree n plus 1. Kill some stuff. To kill a, oh, sorry, we used that expression. So, such that the boundary of what you adjoined, xn plus 1, is a set of cycles generating what the homology you're trying to kill. So at this point, you're trying to kill Hn of what you made so far. So what did you make so far? Not all of X. We've only adjoined degree up to, what did you say? I'm actually deaf. So we're joining xn plus 1 to kill the nth homology. We killed the n minus 1 homology by adjoining what? N. So we have adjoined up to n. Okay, there. That's what we have so far, and then the nth homology. Okay. Oh, sorry. I'm supposed to be doing both proofs at the same time. Or Hn of R square bracket at y less than or equal to n. Close. Okay. So there you go. It's just like the example. So it's Okay, so now you could start talking about trying to do a better job by taking minimal generators at each step. Why not? Take as few generators of homology on every step, then you have to adjoin few variables, right? So that has a name. So I'll just give you the name. When you do it well and efficiently, it has a name. So a minimal model of S over R, I'll just do like that, of S over R is, I'll just use that name, a resolvent created with minimal choices, choices of generators. Okay, and a resolvent. Okay, and then an acyclic closure is a Tate resolution. So the second one, divided power of 1 with minimal choices again, with minimal choices. Okay, so every homology, take a minimal generating state for the homology and lift it to some cycles that generate cycles. Yes. Yes.
One, so by minimal, you literally just mean like the smallest.
Yeah, take the minimal generating. Oh, very good point. So maybe we should be local for this definition. You should shout in the back. You know. Sorry. Let's take R to S a local now, which means that R, so that R and S are local rings.
Minimal, like
in the sense of minimal set of generators of the homology, or not in the sense of a minimal resolution.
Yeah. Okay. That's
good.
Yeah.
So that's so. Note these may not end up being, thank you, minimal resolutions. So if you write out the complex, the differential, so you may maybe you may have the boundary of each, like Fi in the resolution is not contained in Fi in this way. That's okay. In fact, these are usually huge. Because every time you adjoin something, you adjoin so much more that they're enormous. So they're usually not minimal.
I had a second question.
Yes, good.
Which was in the like proof of the theorem, how do we know that when we adjoin things at a later step, we're not going to create more homology? Like how do we know?
Good.
We can stop?
So suppose, good question. So her question is, if you adjoin a variable here, does it mess up something that you? So it won't mess up anything in the earlier in the complex because it doesn't hit that. Later, it might give you more and more homology, but also who cares? Because as you sweep along, you will kill it too. It might be more work, and that's why these are so huge. That's exactly why.
But like it might be, the process might not terminate.
And the process will usually not terminate. So my example was a very special example. Yes. Very good question.
So these are more like theoretical. In practice, it might be hard to actually construct.
In practice, thank you. In practice, it might be hard to construct. In practice, it's impossible to construct.
Is it like, sorry.
And we don't even know like properties of it very much. Yeah.
Is it the kind of thing where it's useful to take a truncation of it? Or is that kind of?
Oh, you mean if you're graded?
Yeah.
A graded truncation? So I don't know the answer. It's a good question. I don't know. Because for free resolutions, it's useful sometimes to truncate and linear some things. Yeah. I don't know graded stuff very well. Do you know in the back?
Did you mean like truncate up to the end step?
No, she means truncate the module in degrees a certain amount up or down.
Well, either.
Yeah. Sometimes when they do free resolutions in the graded world, they don't just look at the module, they look at the module cutting off the lower degree pieces, and they resolve that, and it helps you resolve the whole module.
Oh, but I think.
Yeah, okay, yeah.
Other people break like Michael.
Hmm?
Michael looks at like.
Michael thinks about this.
Yeah, so some people.
That's true.
You tell like physical property.
Oh, that's true.
But you're still, maybe that wasn't the question, but it's still infinite. You're still gonna.
It's still,
even if you cut out the module,
it doesn't matter what you do, it's going to be horrible. But that is a technique, that's true. So Michael is looking at some questions like that. If something stops in certain degrees, does it stop? Does it stop? But it's not truncating the module, but it's asking things like if in certain degrees there's nothing, does that mean there's also nothing later in certain other degrees? But that's not your question. But anyway, yeah. So you might want to look at Michael de Bellevue's recent work because he did I don't know if it's out yet. It's not out yet. Okay. Well, anyway. Okay. Oh, this is why I have such a hard time lecturing. Let's see. 10 minutes. No, but that's good. Okay, so in characteristic 0, these are the same thing. Good? So if R contains the rational numbers, then these are the same. Because divided powers are, adjoining divided powers is just adjoining the polynomial ring. It's always, but anyway, always, you always have that even though x parenthesis n is not xn over n factorial, it is true that n factorial times xn is x to the n. You still have power. You still have regular powers in the divided power algebra because you can multiply. It's an algebra. It just needs x times x. Okay, and they're equal to this, but you can't get to this from x by multiplying x together. And also, I'm doing everything in this week for R to S. One can actually start with a DG algebra here, entering S, and resolve. I'm not covering any of that because it just gets even worse, to explain, but it's the same results.
We're using divided powers mostly when we have characteristic P, right?
Well, in the sense that if in characteristic 0, they're the same thing. So you're always using them then.
If n is greater than or equal to P, wouldn't n factorial divided power?
So some of them are fine, but the problem is you'll always have some powers that are bad. Like in characteristic P, x to the P, you can't do over P. So there'll always be something bad in characteristic P somewhere. Yeah. Some of them will exist, but some of them won't. I mean, some of them will equal blah over n factorial, but whenever n factorial has the P in it, you have a problem.
Okay. And then you switch to doing polynomial variables at that step.
I mean, you were really just doing no, because when you join a variable in characteristic P, an even degree variable, it's going to have a problem somewhere. Some power of it is going to be problematic. I mean, problematic only in the sense of inefficient and cause extra cycles. So you would always do divided if you're just resolving. If you're creating a homotopy algebra, you're doing something else, but I'll tell you about that later this week, maybe on Friday. Okay, let's see. So I think I'm going to start with, I'm going to end running with, I'm going to see what I can fit. So lifting lemma, this is good because someone asked about this. So is there a sort of a universal mapping property? And there is. So, and this one, and it gives you some sort of uniqueness.
Victoria, can I ask a question?
Yeah.
So,
can you ask after or no? Yeah, go ahead.
Just quick.
Okay.
So the difference between the minimum model and a second closure is whether you choose.
Divided by, this used divided powers. Powers, this one used poly. That's the only difference. Okay, so lifting lemma, number 2, tells you the uniqueness of the minimal model up to a linear homotopy at least. So up to homotopy, I'll just say, because that's good enough. So, all right, so it says that if you have A of adjoin Y, so I'm doing the poly version first, it's a semi-free extension of a DG algebra A. I mean, we're mostly doing it for a ring R, but whatever, okay? Then in the category, because I don't want to keep saying all the maps are whatever, of DG algebras, you get a diagram. So if you have a surjective map from B to C, that's a quasi-iso, and so you have a map here called G. So for all maps G, and all maps F coming from this A of Y, these are all DG algebra maps because I'm in this category. I don't want to keep saying it.
A algebra.
Sorry?
DG algebra.
Thank you. I always do this. DG A algebras, which I didn't exactly define. Okay. If A is R, then I did define. Except I didn't really say that either. I didn't say anything about a base ring. Okay. So I kind of defined DG algebras like over Z invisibly, but they could be R modules, R algebras instead, and that would be fine too, and that's what I didn't say. Okay. Then there exists a unique map. Sorry, there exists a map H here that is at least, and H is unique up to a linear homotopy, an A linear homotopy. And there's another lifting map for the other, but you have to be a little more careful. So lifting, woo, and then I will stop. Lifting lemma 3 is a little harder to say, but I'm gonna say it. It's a similar one for semi-free gamma extensions. So like, A of X. Again, it'll live through a diagram like that, but the problem is that this guy has divided powers, and you don't know where to send them unless these guys had a way of taking what are called divided powers of elements. These don't have variables in them anymore, but if there exists something that acts like a divided power of every element, every even degree element in here, then you get the same thing. So, but you need to work in the category of DG gamma algebras, they're called, which just means they have with a divided power structure, which I'm not going to define. It means that all the elements of even degree have there exist elements that act like their divided powers would, meaning they multiply the way you would expect. They differentiate the way you would expect, whatever. So in that category, there's also a lifting thing from here, which is kind of horrible because it's like, how are you going to have that? But if B and C themselves look like A of X type things, then they have divided powers. And so that's why this one will also give you uniqueness of acyclic closure up to homotopy, actually up to nice homotopy. So that's actually, but one more thing I want to say is the cool thing is that it's like a horrible that you mean divided powers where you're going, and you want to make maps from your. This should remind you of an algebra. You have a ring, a polynomial ring, and you want to make a map from it. It's very easy. You just figure out where to send the variables. This is pretty much the same statement. Okay, essentially you figure out where the y's go, you sort of, so you have to be a little more careful, but you sort of undo that, and that's not quite true. But and then you figure out what it's in. Right. But here you're like, oh no, I need a divided power structure on B and C. But only if you have even degree variables. If you have the Kazoo complex, it has only degree 1 variables, and you don't really need a divided power structure on B and C. So for the Kazoo complex, we get this without requiring, well, actually you could just consider it, well, okay, fine. Without requiring divided powers, and the reason is that you can just apply this result. Because it's also, the semi-free extensions allows exterior variables. Okay? It's just that we might be writing brackets, so we might be like, wait, I'm in this situation, but exterior variables don't care which situation they're in. Okay, that's it. Sorry I ran over.
Are there any questions?
Yeah.
Just to make sure I understand the statement of lemma 2. So A, Y is the semi-free extension of A.
It's not a resolvent. It doesn't have to resolve it. It's just, you just added variables in the kill cycles. Okay.
Because I'm a bit lost about B and C. Just any two.
Oh, in the category of DG algebras, meaning they're DG algebras, and that's a DG algebra homomorphism.
But it's an
and that's a DG algebra homomorphism. Huh?
Is G a quasi-isomorphism?
And this one's also quasi-isomorphism and surjective, which I didn't write in words. Maybe I should have. I have a, sorry, maybe I should have written G, quasi-iso, and surjective. Yeah, so it doesn't, it's not really totally free.
Okay. I see.
Yeah, it was like really free, like you wouldn't need these conditions, just a surjection and it would lift, but.
Does B also need to be bounded?
What?
Does B also need to be bounded?
Oh, shoot. Everything needs to be bounded below.
Okay.
Yes. Bounded below. Assume bounded below. How about we assume that for the rest of the week? I do most forget. I'm sorry. I'm terrible with this. Okay, good. All right.
Are there more questions?
Oh, yeah, sorry. You can also ask me when you see me.
So if not, I would like to remind you that at 2:30 we have only one problem session. Everybody will be here working with Josh. And then in the last block, where it was the other problem session, Claudia is going to give the next lecture.
I'm sorry.
Okay?
Okay.
So let's thank Claudia.